Good day, everyone. We're diving into the fascinating world of sequence-to-sequence models with the paper Order Matters, Sequence-to-Sequence for Sets. This research, led by Oriol Vignoles, Sami Bengio, and Manjunath Kudlur from Google Brain, explores the intriguing role of order in LSTM performance and how we can effectively handle unordered data. Stay tuned as we unravel the impact of data order on LSTM's ability to model long-term dependencies and the innovative solutions proposed to tackle these challenges. Our research emphasizes the significance of order in sequential data representation for optimal performance. Long short-term memory networks, or LSTMs, have proven to be powerful models in this regard. They can handle variable-length sequential data and manage long-term dependencies effectively. However, we also delve into the challenges of unordered data, both as inputs and outputs. To address this, we propose the read, process, and write architecture. This innovative approach allows us to handle unordered input data effectively. Furthermore, we introduce an efficient training algorithm. This algorithm is unique as it includes a search over possible orders during both training and inference. This approach allows us to handle unordered output data more effectively, paving the way for more robust and versatile models. Our research highlights two key areas. Firstly, we conducted experiments with the Penn Tree Bank dataset, a standard benchmark for language modeling. Despite its small size, we found that even when we introduced a confounding ordering, such as a 3-word reversal, the performance only degraded by 10 perplexity points. This is a testament to the robustness of our models. Secondly, we delved into the capabilities of long short-term memory networks, or LSTMs. These networks are adept at decomposing joint distributions, even when faced with awkward orderings. This makes them a powerful tool for handling long-term dependencies in data. In essence, our research underscores the resilience of LSTMs in language modeling tasks and the potential of unconventional data orderings in challenging these models. Deep architectures have revolutionized various fields, delivering state-of-the-art performance in tasks such as image classification and speech recognition. They've also made significant strides in machine translation and image captioning. These architectures, including recurrent neural networks and long short-term memory networks, excel in handling sequential tasks. But what happens when the data doesn't have a natural order? How do we represent such data? This is the question we aim to answer in our research. We explore the impact of order in data representation and propose two approaches for handling unordered datasets. Let's delve into this fascinating topic, starting with a look at our read, process, and write model, depicted in the figure here. This model forms the backbone of our exploration into the significance of order in data representation. Recurrent neural networks and long short-term memory networks, or LSTMs, have shown impressive performance on tasks that are inherently sequential. This is achieved through the sequence-to-sequence, or sec-to-sec, architecture. Here, the input is fully absorbed by an encoder, and the final state of this encoder is then used by a decoder, LSTM, to generate the target sequence. However, we encounter challenges when dealing with data that isn't naturally organized as a sequence. How do we determine an order for such data? This is a crucial question, as the order in which data is presented to the model can significantly influence performance. So even when dealing with non-sequential data, we must consider that order matters. Our research has a dual purpose. Firstly, we aim to demonstrate that the order of data matters, even when there's no apparent natural order. Secondly, we propose two novel approaches to handle sets as inputs or outputs in our models. Existing models face several challenges. They often struggle with the small size of standard language modeling benchmarks, such as the Penn Tree Bank. They also have difficulty dealing with unordered input or output data and can stumble when faced with awkward orderings of data. To address these issues, we've developed two methods. The first is the read, process, and write architecture, designed specifically for unordered input data. The second is an efficient training algorithm tailored for unordered output data. These methods aim to enhance the performance of models dealing with unordered datasets. Our research introduces two novel methods to handle data where no natural order is apparent. The first is the read, process, and write architecture, specifically designed for unordered input data. This architecture reads the input, processes it, and then writes the output, effectively handling the challenge of unordered data. The second method is an efficient training algorithm tailored for unordered output data. This algorithm optimizes the learning process, taking into account the lack of a specific order in the output data. Let's delve deeper into the read, process, and write architecture. This innovative approach is designed to handle unordered input data. It processes the input in a way that doesn't rely on a specific order and then writes the output, providing a solution to the challenge of unordered data. These methods have the potential to significantly improve the performance of models dealing with unordered data, opening up new possibilities in the field of machine learning. Our research introduces an efficient training algorithm specifically designed for unordered output data. This algorithm is unique as it incorporates a search over possible orders during both training and inference stages. This approach allows us to handle datasets where the order of elements is not predetermined or fixed. We also leverage the chain rule in our proposed method. This rule plays a crucial role in serializing output random variables, enabling us to handle variable-length sequential data effectively. Furthermore, the chain rule aids in efficiently decomposing joint distributions, which is a key aspect of our model's ability to handle complex data structures. In essence, our research combines innovative algorithm design with established mathematical principles to tackle the challenges of unordered data in language modeling and graphical models. In our research, we leverage the power of LSTM networks. These networks are key in modeling long-term correlations, which is crucial when dealing with variable-length sequential data. Now let's delve into the design of our experiment. We utilize the Pentree Bank dataset, a standard benchmark in language modeling. However, it's worth noting that this dataset is relatively small, often leaving models data-starved. Our evaluation metric was perplexity, a measure of how well a probability model predicts a sample. We experimented with 3 different orderings of the data: natural, reverse, and a fixed 3-word reversal. This allowed us to observe the impact of data ordering on the model's performance. Intriguingly, we found that even when the data order was scrambled, the model still achieved impressive results, albeit with some degradation. This highlights the robustness of LSTM networks and their potential in handling complex sequential tasks. Our research presents key improvements over previous approaches, particularly in addressing the challenges of handling unordered input and output data. We've developed a method that effectively handles awkward orderings of data, a significant stride in the field of language modeling. Now let's delve into some key findings from our experiments. We found that even a confounding ordering, like a 3-word reversal, only degrades performance by 10 perplexity points. This is a testament to the robustness of our proposed method. Furthermore, our experiments demonstrate the effectiveness of our approach in handling different orderings of data, further solidifying its potential for practical applications. In essence, our research not only addresses a significant challenge in language modeling, but also provides a robust solution that performs well even in less than ideal conditions. Our technical results reveal some fascinating insights. Firstly, the order of data has a significant impact on LSTM performance. This was evident when we experimented with different orderings of the Pentree Bank dataset. Interestingly, even a 3-word reversal ordering only degraded LSTM performance by a mere 10 perplexity points. This highlights the robustness of LSTMs in handling awkward orderings. We also proposed methods for dealing with unordered data, which showed promising results. This is a significant step forward as it opens up new possibilities for handling data where an obvious order cannot be determined. LSTMs have demonstrated their power in handling long-term dependencies and efficiently decomposing joint distributions. This ability is crucial for representing variable-length sequential data, a common challenge in many real-world applications. Now, let's consider the implications of these results. The fact that careful data ordering can optimize LSTM performance means that we can potentially enhance the effectiveness of our models by simply reordering our data. The robustness of LSTMs, as demonstrated by their impressive performance despite awkward orderings, is a testament to their versatility. This robustness, combined with the successful handling of unordered data, indicates the potential of our proposed architectures and algorithms. Finally, the ability of LSTMs to handle long-term dependencies underscores their power in modeling variable-length sequential data. This is a key strength that sets them apart in the field of deep learning. In our research, we've made significant strides in addressing the challenges of representing variable-length sequential data using long short-term memory networks, or LSTMs. We've delved into the impact of order on LSTM performance, demonstrating that even when no natural order is known among input or output objects, there might still be one that yields better performance. Take a look at this figure. It shows depth-first and breadth-first linearizations of a parse tree, illustrating how different data orderings can affect LSTM performance. We've also investigated how to handle unordered input and output data, proposing new architectures and training algorithms to tackle these issues. Our work has further demonstrated LSTM's ability to handle long-term dependencies and efficiently decompose joint distributions. In conclusion, our research underscores the importance of order in data representation and the power of LSTMs in handling complex sequential data.